Hello and welcome back. My name is Dr. Garuma Abdisa, and in this specific tutorial we will cover the mirror equation. Let us begin with concave mirror. Concave mirror is a mirror in which the outer surface of a portion of a sphere is silvered or coated. If we assume this concave mirror, the line passing through the center at point V is called the principal axis. This is the focus, and this is the center of curvature. That is, a ray parallel to the principal axis is reflected through the focus. This is something very important to notice while we try to figure out where image is created by a concave mirror later on. Secondly, a ray passing through the focus is reflected parallel to the principal axis. Thirdly, a ray passing through the center of curvature is reflected back through the center of curvature. Fourthly, a ray to the vertex V is reflected, forming equal angles with the optic axis. So the fourth point says a ray to the vertex V is reflected, forming equal angles with the optic axis. That means these two angles must be the same, because those are simply angle of incidence and angle of reflection. Image characteristics of a concave mirror. Number one, the first case, for an image placed between center of curvature C and the focal point F, then the image is real, inverted, and enlarged. So if this is a principal axis, this is C and F. If we have an object O here, this ray is coming parallel to the principal axis and it is reflected passing through the focus. And this is already coming through the focus and is reflected parallel to the principal axis. So this is where the image is created, and as you can clearly see, the image is real, is inverted, and it is enlarged. Secondly, for an image placed beyond C, the image is real, inverted, and diminished, and I will demonstrate that to you. This is the concave mirror. Then this is the principal axis, this is C, this is F. C and F are center of curvature and the focal points. If this is the position of our object, because it is given to be beyond C, this axis has to be reflected through the focus, and a ray that is already going through the focus is reflected parallel to the principal axis, and this is the place where image is created. And as you can clearly see, this image is real, is inverted, and it is diminished. Thirdly, for an image placed at C, the image is real, inverted, and the same size as the object. And if this is our concave mirror, once again, this is the principal axis, this is C and F. If the object is placed exactly at place of C, then this ray is reflected through the focus as usual. Then a ray which is already going through F is reflected parallel to the principal axis, and this is exactly where the image is created. And as you can see, both the image and the object are in the same position, and the image created is real, it's inverted, and it is in the same size. Fourthly, for an image placed at F, that is at the focal point, the image is real, inverted, and highly enlarged at infinity. This is our concave mirror, the principal axis, C and F points. If our object is originally placed at F, this ray is reflected passing through the focus upon reflection, and a ray which is heading towards the optic center is reflected in this way, because the angle of incidence here must be equal to the angle of reflection here. this angle above the principal axis must also create the same angle upon reflection, because the angle of incidence must be equal to the angle of reflection. And as you can see, in fact, we cannot see any image now because the image is created at infinity, but we expect this image to be real. It will be inverted. It will be highly enlarged, and that is created at infinity. So this is the image characteristic whenever the image is placed at f, then such image may not be observable. Fifthly, for an image placed between f and the mirror, the image is virtual, erect, that means upright, and enlarged. If this is our concave mirror, this is the principal axis, C and F. If our object in this case is placed between the focal point F and the mirror, this ray coming parallel to the principal axis is reflected going through the focus as usual, and this ray is reflected leaving the same angle with the principal axis in this way, and this ray is reflected back on itself because it is passing through C. A ray that is going through the center of curvature is always reflected back on itself. And these rays appear as if they are coming from beyond the mirror at the other point, so the image is created on the back side of the mirror. That is indicative of the fact that this image is actually virtual, and this image is virtual, it is erect or upright, it is enlarged. So that is the image characteristic whenever the image is between the focal point F and the mirror. Now let us see a mirror equation for a concave mirror that is mathematically arriving at the same conditions that we have covered so far. So carefully notice this diagram. And from figure A, that is the above figure that you see here, triangle ABH is similar to triangle EBD. Triangle ABH means is A, B is here, and H is here. Is similar to triangle E, B, and D. These shaded triangles, the above shaded and the lower shaded with different colors. So if these two triangles are similar, then AH divided by ED, that is the corresponding sides must be proportional. AH over ED must be HB over DB. And this implies that the O over I, that is the height of the object and height of the image, must be equal to SO over SI. That is this object distance SO and the image distance SI. And from figure B, likewise, because now we consider the distance between these G and the J, this dotted line, and the B, that is the curvature of the concave mirror, is considered to be negligible. We will consider that distance GB to be negligible. And consequently, because these shaded triangles, triangle AHF and the triangle JGF are similar, and the corresponding ratios of a similar triangle must be proportional. From that, AH divided by JG is equal to HF divided by GF. Have a nice look at, so that you can infer from these two shaded triangles. And consequently, O over I, that is object height, and divided by the image height must be the same. But HF, this HF is already equal to, HF means is H to F. This is already equal to object distance, that is from here to there, the same here, object distance minus the focal point. And the GF is simply equal to F, this F. So O over I, object height divided by image height, is equal to SO, the object distance, minus the focal length F divided by F, the focal length. This is our equation 2. And remember that from the first equation we also got O over I is equal to S naught over SI. And from the second equation, O over I is equal to S naught minus F over F. So O over I is equal to S naught over SI, that is the first equation. O over I is equal to S naught minus F over F. That is the second equation. Equating equation 1 and equation 2, we have, solving these two equations together, S naught over I is equal to S naught minus F divided by F. So we can rewrite this equation in this form, and finally dividing both sides by 1 over S naught, we can eliminate S naught and we can simply write 1 over Si is equal to 1 over F minus 1 over S naught, or rearranging their positions, we can rewrite 1 over F is equal to 1 over S naught plus 1 over Si, where F is the focal length, S naught is object distance, and Si is image distance. This is mirror equation for a concave mirror. Likewise, we can also continue the derivation with a convex mirror, and finally we will mix them together so that we can solve them using some sign convention later. Now a convex mirror is this kind of mirror where this side is the silvered side, it is coated with silver, and this side is the reflecting side. So this kind of convex mirror, this is the principal axis, this is the focus, and this is the center of curvature, and the reflecting side is actually from this side, and this kind of ray is reflected this way as if it is coming from the focal point. So a ray parallel to the axis is reflected as if it came from the focal point. Secondly, this kind of ray also appears as if it is coming from because of that, a ray heading towards the center of curvature is reflected back on itself because it is directly heading toward the C. That is, this line is heading toward the C, that is the center of curvature. A ray which is heading this way also appears as if it is coming from F, so a ray heading towards the focal point is reflected parallel to the principal axis. Now let us see image characteristics of this kind of convex mirror. This is the principal axis, focal point and center of curvature C. If this is our object, this ray is reflected as if it is coming from the focal point, and this ray is reflected back on itself because it appears as if it is passing through C. So this is the point at which the image is created. And as you can clearly observe, image formed by a convex mirror is always, irrespective of where you put your object, is always virtual, is always erect, is always diminished. So this is the image characteristic of a convex mirror. Mirror equation for a convex mirror. Now let us see derivation of the mirror equation for a convex mirror as we did previously for a concave mirror, and finally we will merge them together later on. From figure A, triangle ABH, that is this triangle ABH, is similar to triangle EBD, that is this triangle EBD. That similarity is using angle similarity of triangles. Then, consequently, AH divided by ED is equal to BH divided by BD. Have your own time to verify that. This is simply coming from the fact that the ratio of the corresponding sides of similar triangles must be proportional. And this implies that O over I, that is simply AH divided by ED, which is O over I, must be object distance divided by image distance. And we can hold this as equation 1. And from this arrangement, once again, that is from figure B, triangle JFG, that is JFG, is similar to triangle EFD. Again, angle similarity of triangles. And from the fact that the corresponding sides of the ratio of corresponding sides of two similar triangles must be congruent, JG divided by ED is equal to FG divided by FD. or this implies that the object height divided by image height from this arrangement is f divided by f minus si. You can clearly see that from this diagram, and we will hold this as equation 2. And remember that the first equation is O over I is S naught over Si. From the second equation, O over I is again F divided by F minus Si. We will continue with these two equations. So equating equation 1 and 2, we will have S naught over Si is equal to F divided by F minus Si. So Si over S naught is equal to F minus Si over F. I made a reciprocal of both of them. So 1 over Si, we will multiply 1 over Si by both sides, and rearranging this equation, we will simply get 1 over S naught minus 1 over Si is equal to minus 1 over F. This is mirror equation for a convex mirror. So this is for a concave mirror that we have derived previously, and this is mirror equation for a convex mirror that we have derived a while ago. And notice that except for signs, the two equations are very much similar. This difference in signs alerts us the fact that the image in case of convex mirror is behind the mirror rather than in front of it. Also, the negative focal length term is the result of the mirrors being convex rather than concave. So because of these very similar equations, except that the signs are only the difference, we can have a convention for their signs so that we can merge these two equations as one, and we will use exactly one equation in both cases. So rather than remembering the two mirror equations, we can set up rules that I have said is a sign convention that allows us to use one formula for both of them. Hence, we can write for all mirrors 1 over F is equal to 1 over S naught plus 1 over Si, and this will be used for all mirrors under some set of rules. That set of rules is called the real is positive sign convention. Real is considered positive, virtual is considered negative. That is concave. For concave mirror, F is positive. For a convex mirror, the focal length F is negative. And we can extend the use of sign convention to interpret whether the image is erect or inverted relative to the object. We will write the equation for magnification with a minus sign. So magnification is minus of Si over S naught, which is equal to minus of Hi divided by H naught, magnification. So magnification is defined as minus Si over S naught or minus Hi over H naught. M, if M is positive, this implies that our image is upright or erect image. If M is negative, the image is inverted image. Moreover, if the absolute value or the magnitude of our M is greater than 1, the image is enlarged or magnified. And if the magnitude of our magnification is less than 1, that is 0 point something, it is diminished. If M is exactly equal to 1, it will be the same size as the object. So let us concretize what we have seen with examples. Example 1, an object is placed A 15 centimeters, B 5 centimeters in front of a concave mirror of radius of curvature 20 centimeters. Calculate the position, nature, and the magnification of the image. The solution is, because focal length is always the radius of curvature divided by 2, which is 20 centimeters divided by 2, which is 10 centimeters. So from A, the object distance is 15 centimeters. So by directly plugging in the equation 1 over F is 1 over S naught plus 1 over Si, we can calculate Si to be 30 centimeters. And because this Si, which is 30 centimeters, is positive, it means that we have got a real image. And M is minus of Si divided by S naught, which is minus 30 centimeters divided by 15 centimeters, which is equal to minus 2. And as you can see, M is minus 2, which is negative. It means that our image must be inverted image. From part B, likewise, S naught is equal to 5 centimeters. And by substituting into our mirror equation directly, we can calculate Si to be minus 10 centimeters. And the Si is negative means the image must be a virtual image. M is equal to minus of Si divided by S naught, which is plus 2. M is positive, implies that the image must be upright or erect image. The second example, a convex mirror with a 100 centimeter radius of curvature is used to reflect light from an object placed 75 centimeters in front of the mirror. Find the location of the image and its magnification. Is the image upright or inverted? So the solution is, once again, the focal length is the radius of curvature r divided by 2, from which we get focal point to be minus 50 centimeters. It is minus because our mirror is convex, and using the sign convention, F is determined to be negative, and the S naught is given to be 75 centimeters. By directly plugging into our unified mirror equation, 1 over F is equal to 1 over S naught plus 1 over Si, we will get Si, that is the image distance, to be minus 30 centimeters. Si is negative, means the image must be virtual image. And the magnification is minus of Si over S naught, which is equal to positive 0.4. M is positive, indicated that the image is upright, and M is equal to 0.4, which is less than 1, means the image must be diminished.